Hello, everyone, and welcome to this panel discussion on privacy preserving machine learning at Microsoft Research Summit 2021. I am Shruti Tople, a senior researcher in the confidential computing team at Microsoft Research Cambridge. And today, joining us are prominent privacy and security researchers from different parts of the world. I am delighted to introduce our panel members, Divya Gupta, Olya Ohrimenko, and Reza Shokri. Divya is a senior researcher at Microsoft Research India, and her research interests in cryptography and its applications in security and privacy. Currently, Divya's work at MSR focuses on secure multi-party computation and blockchains, and in particular, making cryptography practical, usable, and performant. She completed her PhD at University of California at Los Angeles, and her PhD dissertation was recognized by the Dissertation Fellowship and Dimitris Charafis Dissertation Award given for outstanding work in engineering sciences, medicine, and natural sciences. Thank you, Divya, for joining us. Next, we have Olya Ohrimenko, who's a senior lecturer at the University of Melbourne that she joined in 2020. And prior to that, she was principal researcher at Microsoft Research in Cambridge, UK, where she started as a postdoctoral researcher in 2014. Her research interests include data privacy, integrity, and security issues that emerge in cloud computing environment and machine learning applications. She has held two research grants from Facebook and is currently a co-investigator on an Osmuri grant. Olya received her PhD degree from Brown University in 2013. Thank you, Olya, for participating in this panel discussion. And finally, we have Reza Shokri, who is a NUS Presidential Young Professor of Computer Science. His research focuses on data privacy and trustworthy machine learning. Reza is the recipient of the IEEE Security and Privacy Test of Time Award 2021 for his paper on quantifying location privacy. He received the Casper Bowden Award for Outstanding Research in Privacy Enhancing Technologies in 2018 for his work on analyzing the privacy risks of machine learning models. He received the Early NUS Career Award 2019, VMware Early Career Faculty Award 2021, and Intel Faculty Research Award 2021. Reza has obtained his PhD from EPFL. Thank you so much, Reza, for agreeing to be a part of this panel discussion. Now, I would like to all of us start having this exciting discussion. We have three interesting questions lined up, and without further ado, I'll start with the first question. What, according to you, are the current capabilities of privacy techniques such as trusted execution environments, homomorphic encryption, multi-party computation, differential privacy for privacy preserving machine learning? And what do you think are still the gaps and limitations that remain? Divya, I'd like to start with you. What are your thoughts?
Ex- uh, Excellent question, Shruti. Let me start by describing the problem of secure inference, which is probably the one of the most extensively studied problem in privacy-preserving machine learning. In this scenario, let's say there's a model owner, say a hospital or some pharma company, who has some pre-trained machine learning model. And on the other hand, there's a client or a patient who has this medical report and wants to learn the prognosis based on this machine learning model. But at the same time, he wants to not reveal his medical report to the model owner, and the model owner wants to do this without ever revealing the model to the client or the patient. And this problem can be solved with different kinds of privacy preserving technologies. And one of them is MPC or secure multi-party computation, which is a cryptographic tool which comes with strong security guarantees that at the end of the protocol, parties only learn the output and output alone and nothing else about the inputs of the other parties. Now, specialized protocols in MPC have been designed for this problem of secure inference. It has gained a lot of popularity, and also developer-friendly usable tools have been developed, like CryptFlow from MSR itself, which can take TensorFlow Onyx model as input and automatically output MPC protocols for secure inference. These tools have been tested on wide variety of neural networks like simple CNNs, ResNet 50 on ImageNet, many models from healthcare space, such as the one including super large teraflop size models like UNet 3D, which do automatic tumor segmentation from 3D CT scans. So all in all, this problem of privacy preserving secure inference, I think is practical today with the kind of technologies which have been developed. Another problem which we keep hearing is that of model validation, in which case, let's say I'm a model, I am a person who has data, and I want to determine whether a model provided by a vendor performs well on my data. And this also falls into the umbrella of privacy preserving machine learning because both the parties involved have natural privacy requirements. And we have also done one such study between the Stanford University, who has the state of the art model for detecting 14 lung diseases from chest x rays, and Caring Labs in India, who has the patient x rays from India. So, this is just gives a flavor of what is possible today with privacy preserving technologies. Now, coming to gaps and limitations, while all I described to you is practical with MPC today, it comes with performance overheads. For example, inference of one chest X-ray takes up to 15 minutes. And this can be practical in some applications and might not be acceptable in some other applications. And given these overheads, for example, today, end-to-end secure training using MPC is not practical. Because think about it, if I'm saying one image takes 15 minutes, then 15 minutes times a million images is a lot of minutes and soon gets intractable.
Thank you, Divya. That's a great input in terms of really what sensitive applications we are looking for and limitations. Now I'll move on to Reza. What are your thoughts based on your experience and expertise?
Yeah, so let me talk about a little bit about the data privacy problem that you have computed a model, let's say you did some statistics about data and you're releasing the model or you're allowing others to have access to the model for predictions. In those scenarios, there are many attacks that show that an adversary would be able to reconstruct information about the individual data records in the training set. And so the definitions that we have for privacy, notably differential privacy, would guarantee that if you train a model under this guarantee, although the model would allow general information about the population to be released, but would limit the amount of information that could be leaked about the individual data records. So something which is very promising here is that this is also the goal of machine learning, right? So when we are training a machine learning algorithm in general, we want to extract the general patterns. We are not that interested in the corner cases. So this is very interesting. It is possible then that designing algorithms which are privacy preserving and accurate at this time. But the challenge is that the tools that we have now would not allow us to do that for large models, right? So there's a gap between what we think we could achieve with certain level of privacy and what we are achieving now. Notably, the issue is that our assessment of the privacy risk is an overestimation of what privacy risk we have for using an algorithm. And I think that the next steps would involve reducing that gap and having a better estimation of privacy risk.
Thank you, Reza. So I think what you're like with respect to gaps and limitations, it's the privacy risks in practice that we have and what theoretical guarantees or the tools that we have right now provide. And that's the gap that we should look at mitigating. Thank you.
Yes.
And yeah, Olya, I would really love to hear your thoughts on what do you think are the capabilities and limitations that still remain with privacy technologies.
Thanks, Shruti. So I will, I guess, more focus first on what Divya has said. So I will focus on the trust execution environment, or TEs, because I've had more experience working with them. So TEs aim to guarantee similar things that Divya has talked during training, inference, but using a different technology. So it's a hardware or software capability, basically to provide isolation for your computation, be it machine learning or anything else, from the rest of the system, from the operating system or from other processes. So it's quite attractive when you want to run something on the cloud and use cloud resources. So we have come actually a long way since 2016 when I was at Microsoft Research working on this, and when we actually ported some of the algorithms in C to be able to run them on Intel SGX. Since then, it's really amazing how much the technology has come. Now we have things like SGX and LKL or Graphene SGX that basically have a way to run things like PyTorch or TensorFlow basically on these TEs. There is, in terms of, I guess, where, and actually they are provided as part of the cloud offerings at Microsoft, Google, and IBM, different types of TEs. So then the question is, I guess, what is the limitations? We have all seen kind of a lot of side channel attack papers in the past 5 years. There is, I think, every conference has, every year there has been at least one attack paper on one of the Ts. But I don't think it is a limitation. I think it's an opportunity actually to create open source designs for Ts, and such as, for example, Sanctum or Keystone for customizable Ts. Why? Because they can be verified by the community because they're publicly available, or even amenable to formal verification. What I do see as a gap is when we want to talk about privacy-preserving machine learning, we need to look at the end-to-end spectrum. So it's not just about performing the computation securely. We need to think what this computation actually reveals, what the output reveals about the input. So consider a pathological example where I read in a string, encrypt it, and then I output it in a reverse order. Even though I did it on encrypted data, the output directly leaks the data. And I think this brings it to the point that Reza was trying to make, is that in order to guarantee, we need the end-to-end privacy, we need to guarantee secure computation and consider how it combines with privacy techniques, for example, with differential privacy. And what I think is also a gap with collaborative learning. When we return an output, when the hospitals are training a machine learning model, for example, can one hospital determine the mortality rate in another hospital's data just by merely getting the output that was computed on their data, even if it was done securely with any of the techniques that, for example, Divya mentioned, or TEs. And here, the question is, how can we still guarantee basically the end-to-end privacy in that setting? And actually, as Shruti and I work together with you and Vendors, and we did show that a party can learn a distribution of, for example, gender in another party's data and so on. So yeah, I think we need to really consider the end-to-end spectrum in order to guarantee privacy.
Thank you, Olya. I think you've made some great points there. Also connecting the responses both from Divya and Reza, that each of these privacy technologies that we know has some capabilities, but also limitations. And maybe it's not just individual technique that will give us an end-to-end privacy-preserving machine learning setup, but a combination of two or more of these. Like differential privacy, you will need to apply it even if you are using computing on encrypted data or with trusted execution as at an end output, and depending on what it reveals. And again, for efficiency, maybe a combination of using trusted execution environments plus MPC would be suitable for some application settings wherever that's desirable, especially for maybe secure training using TEs and then secure inference using applied cryptography. That's great. Is there any other thing that you would want to add or a last comment for specifically discussion on this topic?
I think my final comment would just be that all these technologies, BTs, MPC, or HE, and so on, they just tell you, given a function which you want to compute, it just tells you what's a secure way of computing it, and they can give you security and performance trade-offs and so on. But I think one needs to really think about what outputs are safe to reveal, and even do you really want to reveal the outputs, or even they should remain hidden and you just want to keep computing on encrypted stuff. So that's, I think, a very important question as to what outputs are safe to reveal and whether you should do it.
I agree. I think that that's a very good point. Just looking at interfaces that will be exposed and then which technology applies there. Thank you, Divya. Moving on to the next question, which I think is in similar flavor, but looking at a more general problem for the industry perspective, which is of data fragmentation that across geopolitical boundaries it is making it more difficult to assemble central training sets. Like data is being generated across different countries, and there are different privacy laws that are applied in each of these. So how can we actually use these technologies to collect centralized training sets? And how can existing techniques that we discussed, or even newer like federated learning or collaborative learning that earlier you mentioned, can play a role in addressing this challenge? Olya, maybe because you've already touched upon the collaborative learning and multi-party setting, you want to start with addressing this question?
Sure, Shruti, thank you. So I think in order to answer this question, we really need to understand what the policy relates to and whether the data actually needs to be transferred. So for example, do I mean about the policy is whether the policy relates to the data or the information about the data that needs to be exchanged. So what I can see is, for example, in a local setting, we have some data and then there is this central server. So then the question is of transferring the data from this local server to the central server and whether it is needed. So besides kind of the techniques that we mentioned, there are actually technologies of transferring, of ways to learn on the data without actually having to transfer it. So one way is federated learning, as you mentioned, right, where the data doesn't have to be transferred. We only compute some gradients and help the central server to aggregate the gradients and compute the model. So that's one way. The second way is methods-based, like for example, Pater framework, where each local there can be local models computed, and then you just answer, for example, to the server, you label some of the data, or you answer some of the central questions and help the model to be computed. So again, in here, we don't transfer the data, but we just transfer some outputs of some computations or some answers to questions. So that's one way. The second way, maybe we actually bring the model to the local device. So there are techniques actually not in security, but in machine learning, such as fine-tuning, right? So we can compute a general central model and then send it to the, for example, if it is a model trained on English language, we can send it somewhere where it is a different language with only thousands of people speaking it, and then train that. So, but the key thing is with both of these technologies is that we do know that even if we don't send the data, we still leak some information about it, right? Or not leak, that we are learning some information about it. So gradients reveal some information about the membership or the properties, right? Sending the model is, as Reza has mentioned, are susceptible to membership attack. So that is why I think the key is to understanding whether the policy is related to information or data, and then use the technology towards solving that.
Great. Thank you, Olya. I think that was a fantastic answer. Really giving us the ideas, but also what are the limitations still, and with respect to really addressing these policies, looking at does it apply to data model, and then looking at what defenses can be used. Thank you. Divya, I would go to you next for looking at an answer for this question.
Thanks, Shruti. Another great question. So, I think you're right that like these regulations which are coming into place more and more are trying to restrict and define what data gets collected, where it is stored, for how long, and what purposes it can be used for, and so on. I think even then these policies are quite primitive. They just try to say some very basic things, that data should be kept encrypted and cannot leave in the clear, and so on, right? So I think that these technologies like MPC and computing on encrypted data and others can actually be used to still derive benefits from data, while ensuring that data in the clear never leaves these geopolitical boundaries. For example, things like only encrypted data leaves the boundaries. So if I just to name technologies like MPC, they can be used to train on encrypted data, when you can have the strong guarantees that only the final model will be revealed, and that too to the agreed upon parties only, and that can also be domain hidden and so on. But it does come with, again, performance overheads. You can do this for some commonly used models like a logistic regression and small DNNs, but performance degrades badly when you go to large models. And as Olya mentioned, right, that federated learning is a technique which has been designed to specifically solve this problem. You don't need to move the data. You don't need to compute jointly. You can just train your models locally and then combine those gradients. But as she mentioned, the issue is that these gradients are getting leaked, right? Now, the question is, what do the gradients reveal about the underlying data itself? And then you can use techniques like differential privacy on top of it to these locally trained models and say that it mitigates some of these attacks. But setting these like parameters of DP gets increasingly challenging as the function you are like, computing gets more and more complex, right? So there are these various technologies which exist out there, which have their own trade-offs. But at the same time, I feel that for any of these technologies to be used in practice, some dialogue needs to happen between the policy makers and the technology creators to be able to understand what is okay and what is not okay. For example, I think a case can be made that it should be okay if only encrypted data leaves the geopolitical boundaries and the key never leaves. So, and encrypted data without key is essentially useless, right? Like you cannot like, decipher the individual data. Or some such things have to come in place, right? Like where the law understands the technology and technology understands the law, and then I think we can come up with the innovative solutions for this problem.
Yeah, that's a great response. Yeah, I think we still need some synergy between the laws and what are the capabilities of technologies. And like there are some strong properties, as you said, right? Without the key, you can't really do anything with the data. You have to bring it back to the country or the area where the key resides. So yep, I think that's the great way to look at how can we address these issues. Reza, I would come to you for a response for this question. What are your thoughts on it?
Yeah, so I think Olya and Divya very well showed the big picture where all these technologies can come together to preserve privacy. But what I want to add and rather highlight are twofold. One is the threat models, and the other one is the settings in which decentralized learning is used. So I've seen many times that the threat models are not well presented, and in many cases, even federated learning is presented and advertised as a privacy-preserving mechanism, which definitely is not. As pointed out before, if you have the simplest and the popular algorithm for federated learning, which is repeated training and sharing the gradients with the server to aggregate and send back, well, the gradient vectors are very high dimensional. They encode a lot of information about the local data, and eventually one would be able to reconstruct all the surprising information which is in the local data, right? Which would violate data privacy. So it's very important to know what is the threat model, even if data doesn't leave the sensitive, whether the sensitive information is could be inferred or not. And the second thing is about the settings in which we use decentralized learning. So all this started with very simple scenarios where everybody has more or less the same type of data and everybody has exactly the same objective. And there is a server that later on could be replaced by TE or secure multi-party computation that just does the aggregation. But as soon as you change the data distribution a little bit, then we'll see that the models don't converge to what they converge in the case of data being distributed beautifully in an IID way. And as soon as you add privacy protection mechanisms like differential private mechanisms, then we are not learning anything. So for example, if you want to learn a language model over multiple parties and gradients, let's say, are randomized at the local level, we don't learn anything. It doesn't converge to anything useful. In many cases, actually, even for the simpler tasks, what we learn with differentially private federated learning is worse than what you learn if you just train on your own data, right? So that is one thing that we need to pay attention to. And there are other aspects. So, for example, there is robustness of federated learning. When you add randomness, then malicious parties can hide in the crowd, because then their malicious manipulation parameters would be indistinguishable from the randomness that DP would add, right? So that's another challenge, right? I think the more realistic scenarios are way more challenging than the original setting when everybody would just share a model in the same way. Yeah.
Yeah, thank you, Reza. I think you made some really good points about looking at the threat model, which is often like the main reason where technologies don't really give the guarantees that they promise, or the way they are being applied. It's just the threat model is not right. And federated learning, looking at it, maybe opens up or solves some problems, but as you said, like robustness or gives more capabilities to users. So it is really important to look at using this technology, what are the pros and cons, and what is the desired outcome from it with respect to both privacy and security. Thank you for these great points. In the interest of time, I'll quickly move on to our next question, and just maybe uh, a thought on what do you think would be great for our audience and people watching this video. So, from the long-term research perspective, what do you think would be directions for research that should be given more attention to improve both security and privacy guarantees of ML models? Reza, because I think you already pointed out some directions, definitely. Would you want to just go ahead?
Yeah, absolutely. So one thing that I've always been advocating, or at least it's my interest as well, is that when we are talking about privacy, we cannot have a privacy preserving system if you don't have the right metrics and tools to evaluate the privacy risk. And it is true that in the ideal world, we might have algorithms and guarantees that privacy is perfectly preserved, accuracy is good. But in the realistic settings, we are far from that. So having a privacy auditing tool would be something that is, I think, necessary to have a way to measure privacy risk. So we have been developing a tool that we call ML Privacy Meter, with exactly this objective that whether in the centralized or in the federated setting, if you want to know how much information is leaked about your training data, you would be able to track that. And that actually could be helpful to evaluate the effective privacy loss that you have, even though if you have a provable privacy guarantee. As I mentioned, the privacy guarantees that we have for differential privacy are usually overestimations of the privacy loss. Something that I want to maybe clarify here is that differential privacy talks about the worst case privacy risk of an algorithm, whereas in practice you have an instance of that algorithm, and then that instance, which is a model, would leak way less than the worst case would leak in that domain of that algorithm, right? So I think it's always good to have those tools to track the privacy loss.
Thanks, Reza. Olya, just quick thoughts. What do you think should we look at next?
I think we might be moving away from individual privacy, whether someone, for example, is positive to the virus or not, versus data set level privacy. So if someone reveals a computation on a whole data set, what are the properties about the data set that are being revealed? And here, in contrast to the example about the attribute of someone, it's the property of the data set. So it's the distribution of how many people, for example, are positive on a certain virus. So, and differential privacy, unfortunately, is not designed to protect that. So I think we need to move on to this property level privacy, because even if like in my data, I don't have that I am a female born in the particular year, just the ratio of the TikTok versus YouTube videos that I share probably will reveal my age. So yeah, this is what I think is moving to the data set level privacy.
Yep, totally agree. I think that's a good point. And Divya, what are your thoughts?
Yeah, so I think I'll say a couple of things. So first one, as I already mentioned, was the dialogue between the lawmakers and the technology makers, right? Which should really help advance this area. The second thing I feel is this the idea of co-design of machine learning and privacy preserving technologies would really benefit the performance and other things of privacy preserving machine learning technologies. Just to give an example, right, that on CPUs, the cost profile of all the primitive operations is the same, right? Additions, multiplications, comparisons, everything costs the same. But for things like MPC, additions are free, multiplications require parties to talk, comparisons, sigmoid, etc., are even more expensive. So when we try to fit custom-made ML algorithms to MPC or other technologies, the performance is very strange, right? We see very counterintuitive results as a machine learning engineer. So I think co-design of ML and technology, like this privacy preserving technologies, would really help bridge this gap. And secondly, I feel that we should invest heavily into coming up with better and stronger attacks against machine learning. So people start to care about security and privacy when they're explicit attacks. For example, a sequence of data breaches on the data like forced people to use encryption at rest, and soon it became a de facto standard. So if we really want people to care about security and privacy of machine learning, we need to have explicit attacks, and then we can get and then it can help us design systems which protect against those attacks. If we don't know what we're protecting against, then all our models are just very theoretical and in the air.
Thanks, Divya. I think motivating research directions both from attack and defenses. That's an excellent point. That was a really great discussion. I would like to thank you all panel members once again for joining us at Avisa Research Summit, and I hope like the audience will really enjoy watching this video when it's out there on October 21st. Thank you.
Thank you.
Thank you so much.
Thank you. Thanks for having us.